In this video, I'm going to look at what it means to have a power with a negative exponent, and we'll look at how to interpret that negative exponent and why it works like that. Okay, so here's the thing. When mathematicians first started using negative exponents, they didn't just get together and just come up with something that they thought would be, oh, this would be fun if negative exponents worked like this. Instead, what they did was they looked at the patterns they already had with the exponents, like positive exponents, that they'd already decided what those meant. And then it turned out that there was only one sort of definition of negative exponents that worked with all the patterns and that worked with the exponent laws and just what we know about arithmetic. So then they said, okay, well that's got to be what negative exponents mean. So I'll come up with this explanation. I'll look at it two different ways. So one of it is just looking at patterns, and another way is using exponent laws. And then at the end of this video, I'll give you a definition of what a negative exponent does. Okay, so suppose we're just going to look at patterns here. Suppose we've got 2 cubed. What's that? Well, that's 8. And then 2 squared is 4, and 2 to the exponent 1 is 2. If we look at what's going on here, how do we get from each line to the next line? We're dividing by 2 as we go down the table. Okay? And this also gets us to 2 to the exponent 0 is 1, which you should know, but you may have forgotten. 2 to the exponent 0 is not 0, it's 1. But then what happens now? If we divide 1 by 2, what do we get? Well, we get a half. And if we divide a half by 2, well, we get a fourth, or a quarter. And if we divide that by 2, we get an eighth. But just take a look at this. If we look at, say, 2 to the negative 3 and compare it to 2 to the exponent 3, look at what those numbers are. And then 2 to the negative 2 compared to 2 squared. And 2 to the negative 1 compared to 2 to the exponent 1. So it turns out that all we do, if we've just got an integer to an exponent, an integer to a negative exponent, it's just 1 over what it would be if the exponent was positive. And this is called the reciprocal of the base. So the reciprocal of 2 is 1 over 2. The reciprocal of 6 is 1 over 6, and so on. So it looks like the negative exponent is just as if it was a positive exponent, but we take the reciprocal, we flip the number upside down. Let's look at some more. So we had 3 over 4 to the exponent 3. So it's 3 cubed is 27, and 4 cubed is 64. Okay, and 3/4 squared is going to be 9 over 16. 3/4 to the exponent 1 is 3/4. And then anything other than 0 to the exponent 0 is 1. And then we'll use the same pattern. What are we doing here? Well, we're dividing every time by 3/4. And this makes sense because if we think about exponents as repeated multiplication, then as we come down the list, we're not multiplying by 3/4 as many times. So it's the same. It makes sense that it's dividing by 3/4. Okay, what's 1 divided by 3/4? I'll just do that up in the corner here. Remember that that's 1 times 4 over 3. Because to divide by a fraction, we flip the second, or take the reciprocal of the second and multiply. So this is 4 over 3. And then you can do all these out if you want. If we divide that by 3/4, it's the same as multiplying by 4 over 3, so we get 16 over 9. And if we do it again, we get 64 over 27. Okay, so let's look again. 3/4 to the exponent negative 3, how does that compare to 3/4 to the exponent positive 3. Well, it's the same number, they're just kind of upside down from each other. It's the reciprocal of 27 over 64. And then we'll do it for the exponent negative 2 and the exponent 2. And they're also just reciprocals of each other, they're upside down from each other. And then for the exponent 1 and negative 1, it's the same thing, they're also reciprocals of each other. Okay. Now I want to give you just another explanation for why this should work. Because maybe you'd think, well, what if the pattern doesn't continue? The pattern doesn't necessarily have to continue. It's nice if it does, but... so here's another way of looking at it. Suppose we took 5 to the exponent 4 divided by 5 to the exponent 7. And 5 could be anything. This explanation works equally well with an x there. And then I just chose two exponents where the exponent in the numerator was smaller than the exponent in the denominator. Now here's why I did that. Because of our exponent laws, we have a quotient of powers. We're dividing two powers, and they have the same base, so we can subtract the exponents. Okay, so that's equal to 5 to the exponent negative 3. So that's why I chose the exponent in the numerator to be smaller, just so we come up with a negative number here. But let's look at another way of writing this. Or this is equal to, so I'm going to just write out what this is. 5 times 5 times 5 times 5. It's 5 to the exponent 4. And then on the bottom, I'm multiplying 7 5s. 1, 2, 3, 4, 5, 6, 7. Okay? And now, like we saw before when we were looking at exponent rules, we can kind of we can simplify this. We'll divide the top and bottom by 5. We can do it again, and again, and again. So all we have left in the numerator is 1, because we've taken, what is this, 625 divided by 5 4 times, and we're left with 1. And then in the denominator, we're left with 3 5s. So I could write that as 125, and I'm going to write it as 5 cubed. So I've taken this initial expression, 5 to the exponent 4 divided by 5 to the exponent 7, and I've simplified it in two different ways. One of the ways gives me 5 to the exponent negative 3, and the other way gives me 1 over 5 cubed. So these have to be the same thing. So here's another example showing that if you have a negative exponent, then it's going to be the same, that expression is equivalent to the reciprocal of the base with that exponent but positive. So same number, so negative 3, but it'll still be 3, but it'll be positive. Okay, so let's write this out as a rule. So this is for x is any real number except not 0. If the base is 0, we get some dividing by 0, and it's a bit of a mess. So the base won't be 0, but it never would be, because we wouldn't run into this if the base was 0. And then this is for any rational n. So x to the negative n is the reciprocal of x to the exponent n. So what that means is you do x to the exponent n and you flip it upside down. i.e. means that is. So we can write x to the exponent negative n equals 1 over x to the n. And it's also useful to know, because if you take a negative and make it negative again, we get positive. So we can just write this. I'm going to write this out explicitly because it helps a little bit. If you have 1 over x to the negative n, that's equal to x to the n. So these two things really mean the same thing. Essentially, this means if you want to change the sign of your exponent, you flip the base. So you take the reciprocal of the base, and then that makes your exponent positive. A common mistake I see is that people remember that negative exponents involve reciprocals or flipping numbers, but they will often take the reciprocal of the exponent, which is not right at all. It's not true that, say, 2 to the negative 3 is equal to 2 to the exponent 1/3. That's not the same at all. So it's equal to 1 over 2 cubed. Okay, so it's the reciprocal of the base. Okay, good luck.